11.2, proving figures are similar using transformations, geometry. Essential question, how can similarity transformations be used to show two figures are similar? So if you go through any transformation you really want, you should have a similar object by the time you're done. So if you, I don't know, let's see, if you go ahead and that's a terrible, terrible circle. There we go. Let's say you translate, okay, with a vector. Okay, if you translate that circle, and you just move it over to the right, it should be a similar figure than the original. Okay, so here's your original, the red one, and then here's the image after you're done. Okay, circle prime. So it should be a similar object, right? A circle, you move it to the right, it's still going to stay a circle. Okay, that's what similarity means. Now, if a sequence of similarity transformations can be shown to map one figure to another, just like the example I drew up there, the figures are similar, okay? So, if you translate a triangle, for example, with a vector, it should be similar, okay? Dimensions should be proportional in some sense, okay? So, definitions. Similarity transformation is a transformation in which an image has the same shape as its pre-image, just like the examples I gave to you a little bit earlier. Now, similarity transformations include transformations you've already learned. One is reflections. Here's an example, okay? I went ahead and gave you two examples just to kind of help you recall the past. This reflection right here is a reflection across the y-axis, okay? And this rule right here is a reflection across the x-axis, okay? Translations. Remember, translations usually give you a vector, okay? Some kind of heading, if you will. All right. Now remember, you just take a point, like this one, and you either go left or right, or up or down, okay? Rotations, here's an example. I went ahead and just rotated our point right here. Okay, and I just spun it around. I rotated by 180 degrees. Remember, if it's 90 degrees, your y and x will swap. They'll change places. But with 180, your x and y just both negate. Okay, that was one of the rules back in the day. Now, dilations, just like in 11.1 that we already covered, this was the rule. Okay. Now, remember, you have to remember your center of dilation, okay, where you're dilating from. But whatever point you're given, you just multiply your x and your y by the scale factor. Remember, k is the scale factor, okay? Okay, two plane figures are similar if and only if one figure can be mapped to the other through one or more similarity transformations. So if you're going to, I'll give you a quick example. If you're going to move or transform a triangle that has a height of 1 and a base of 2, okay, if you transform it, you either translate it, you reflect it, you rotate it, you dilate it, it should have some kind of similar ratio to its distances. So what would be similar in this situation is a 2 to, let's say, a 4. Okay? Notice how we're just dilating by a scale factor of 2. Okay? 1 times 2, 2 times 2, and that's what gives you the same ratio. Now, if it wasn't similar, it would be visually very obvious. Your triangle would come out, and let me do an even worse example. Okay, and then all of a sudden this guy becomes a 4, and this guy becomes a 2. Actually, not a 2. I'll give you a way more awkward number that doesn't even make sense. We'll do, yeah, a ridiculous big number. Okay, so it would just like, what happened? That doesn't make sense. Okay, that's a good example of things not being similar. Or even if it's not even the same object, like it's not even a triangle anymore, it's just turned into a circle. All right. So in example 1. In example 1, we'll have a triangle. Okay. Here, I think we go, you'll have a triangle like this. Okay. Now, they're going to give you another triangle, except this time slightly smaller. And they're basically going to ask you to describe the transformation so that you can map the green guy, the green triangle, to the blue triangle, or to the red triangle. Okay? And what does this confirm about the triangles? All right? Basically, it's asking what transformation was this? Okay? And is the green triangle similar to the red triangle? Now, it looks like we dilated, okay? So I think our transformation here is definitely a dilation. Now, visually, you should be like, hey, it looks like your scale factor looks like a half, right? It looks like the red guy is like half of the green guy. If you want to double check yourself, you can actually look at the distance, okay? Your distance, for example, for the base of the green guy was 12, right? From -4 to 8. So that was a distance of 12. And for the red guy, his distance was 6. Okay, you went from 12 to 6, and they look similar. You know, they look like everything is kind of same, just a little bit smaller. So our scale factor here, remember K could represent scale factor. So K equals 1/2. And it looks like both are similar, okay? In fact, let me go ahead and be thorough about this. Both red triangle and green triangle are similar. If you don't believe me, double check your distances on all the other sides. And remember, they should all have the same scale factor of 1/2. Okay? And that's an example of a similar transformation for these two triangles. And in the end, both of them are similar. Okay? Now, in example 2, I can go ahead and show you one that is not similar. Okay? So, let's go ahead and start with a triangle. Okay, we're going to start with, let's say, yeah, let's start with a triangle. Or not a triangle, a rectangle. Rectangle would be better. All right, so here's our rectangle. Now, if we look at a transformation that gives us a different triangle, we'll say, let's see. So we did apparently there was a sequence. Okay, something happened. We rotated. It looks like a rotation, right, at the origin by 180 degrees. Okay, but are they similar? Okay, well, let's look. Our dimensions for the red rectangle, he's got a height of 2, okay, and his width, okay, is 4. Okay, so he has a length of 2 and a width of 4. Okay, well, let's look at our blue guy, or our green guy. His length is 3, and his width is 4. That doesn't make sense. We just rotated. Why aren't they matching up? Okay, so this is an example of when your two images are not similar. Okay, it looks like a rotation by 180 degrees, but when you look at their dimensions, okay, they're not going through a dilation because, I mean, why would the 4s still be the same, but the 2 and the 3 are, they're different? Why are their widths the same, but their lengths are different? Dilation would change all the dimensions, okay? So obviously that didn't happen. Therefore, these guys are not similar, okay? So this is an example of not similar. All right, for example 3, we're going to go ahead and we're going to do a dilation. Okay, we're going to dilate this rectangle. Okay, obviously it's got a length of 3 and a width of 2. Okay, and we're going to dilate it from the origin. We're going to go ahead and do that. So if we dilate from the origin, And we'll talk about the scale factor that I used here. I'm going to go ahead and go by 2. So if I multiply this point right here by a scale factor of 2, I'll get 2 comma 2. And if I go ahead and multiply this point by a scale factor of 2, I'm going to get 2 comma 8, which is right there. If I take care of this point and multiply it by 2, okay, that's 3 comma 1. So 2 times 3 is 6, and 2 times 1 is 2. So that's the point for that guy. And then if I multiply this last coordinate, 3 comma 4, by a scale factor of 2, it's going to be 6 comma 8. That's right there. So your new rectangle, that's a terrible, terrible line. I don't know why I want to be a perfectionist right now. All right, so that terrible, terrible rectangle, pretend it's perfect, okay, just went through dilation, okay? And again, it's a dilation with a scale factor or by a scale factor. And again, if you're lazy, use K to represent scale factor of 2, okay? So are they similar? Well, let's look at the dimensions for the red rectangle. Okay, his length is definitely 6. Okay, and his width is 4. So remember, if they're similar, they have the same proportions, the same ratios. So remember, they went through scale factors of 2. So this 3 became a 6 because 3 times 2, right? This width was a 2 for the green guy and went through a scale factor of 2 as well and became a 4. Okay? And they have the same ratios because, for example, his ratios was 2 by 3 for the, and let me change the colors. Let's stay color coded here. The green guy was 2 by 3, okay, for his dimensions, while the red guy actually has the same dimensions. Well, they're different. They went through a dilation, but if you know how to reduce, they have that same proportionality, okay? So, in the end, you would just say that your green triangle or triangle, why am I saying triangle? Your green rectangle and your red rectangle are similar. They both underwent a similarity transformation of a dilation by a scale factor of 2. Okay? All right, so example 4, we're going to go ahead and have triangles again. This time I mean it, actual triangles. We're going to go ahead and put them, let's say, I'll just go ahead and make a isosceles triangle. Remember, isosceles triangle means that 2 sides are the same. Okay? And then you go through a transformation of an object, and they'll probably give it to you in your homework. They'll give you 2 objects, one pre-image and one the final image. And they're going to ask you if it underwent a similarity transformation, okay, and whether or not they're similar. So let's go through our new drawing. for our new image, okay, that just underwent its transformation, okay? Now, are these guys similar? Is the red triangle similar to the green triangle? Well, I don't think so. I think something changed just visually looking at it, okay? The bases look, um, you know, similar, but something's different, okay? We have an isosceles triangle here, okay? But this guy, the green guy, it doesn't look like an isosceles. It's not, okay? If we look at the angles, okay, if you measure it on a protractor, these angles, not only are the sides not the same, but the angles are off too. Okay, those two angles are the same because it's an isosceles. And you have this bigger guy right here, okay? And if you look at the green guy, obviously it doesn't have the same proportionality with the angles. So your answer for this is the red triangle and the green triangle are not similar. And that's because they're angles. Their angles they're not the same. And your homework focuses a lot on that. And if you think about transformations, you know, that's not really preserving any proportionality with the other triangles together. It's something definitely warped your triangle. Okay. So the last example I'm going to give you is a parallelogram, and we're going to start with this nice little parallelogram. Right here, okay? And then all of a sudden they give you another object, another parallelogram. Kind of looks like a flag. Okay, but just pretend they're perfectly aligned. I know the drawings are a little rough. I probably will evolve a bit. I just like practicing, I guess. Okay, so you're going to get a picture like this on your homework type deal, and they're going to ask you, is there a similarity transformation that can occur here, and whether or not the green parallelogram is similar to the red parallelogram. And of course, they're going to label them with points, but the idea is the same. So, if we look, I believe in the textbook, speaking of points, and points are kind of important, especially when you look for center of dilation, okay, center point for dilation. They call this one point F. This is point T. And this is point U. And this is point V. And then they give you point E, point D, and point C. Okay. Obviously, it looks like it's the same parallelogram. It just got bigger. Okay. And it did. Okay. Now, it went through a dilation by a scale factor of 2. Okay. And that was centered at the point F. And that's why the points are significant enough to mention. Okay. It's no longer at the origin. It's just expanding outward from point F. Okay, and that's what we mean by the center. It's just, it's like, here's your flashlight. And you're just reflecting a big, huge shadow off the green parallelogram. Okay. Are they similar? Yes. Your red parallelogram and your green parallelogram are similar. They even have the same properties. The scale factor occur to every length in your object. Originally, your length was 2 for the green guy, and its width was 3. That's a terrible, terrible 3. 3s have a tough time on a touchscreen. Okay, and then your red guy has a similar ratio of 4 for his length, but his width is 6. Okay, similar proportions. And that can be said with all their sides. So that's why they're similar. Fun fact, proving all circles are similar. All right, so all circles are similar by the circle similarity theorem. Okay, the only thing that changes is through dilation. Or even vice versa, going the other way, getting smaller. The only thing that changes, again, is their radius. But it's still a circle, okay? Anybody like Pac-Man? Nom, 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 nom. All right, so that's just a fun fact. I don't think there's any problems like that on homework, but it would be a fun little quiz question. Wink, wink. All right, so I'll be right there. Questions. These are the questions I want you to look at and answer and turn it into me on haiku. First one, what kind of transformations result in similar figures? Okay, I listed them. Are dilations the only transformations that result in an image that is similar to the pre-image? Explain. Okay, are there any other transformations that can result in similar images? Okay. Here's your homework. Best of luck.